All right, let's dive right into this explainer and build a physics tool belt that's going to let you literally predict the future. And no, I'm not talking about some magic crystal ball here. We're talking about using the fundamental laws of how things move. Whether it's a cheetah sprinting across the savannah, a train slamming on its brakes, or honestly just you walking down the street, motion governs everything. By the end of our time together today, you are going to possess the exact mathematical tools required to analyze, understand, and predict the precise position and speed of objects in motion. But hey, before we get to those heavy-hitting predictive equations, let's start with a little trapdoor question, just to test your instincts. Picture a really hungry sheep. In pursuit of some tasty grass, this sheep walks 10 kilometers east, takes a right turn and walks 5 kilometers south, and then takes another right turn and walks 10 kilometers west. Here's the question. How far did that sheep really travel? Keep your answer in the back of your head, because depending on how you look at the world, there are actually two totally valid answers. Here's our roadmap for leveling up your physics skills today. We'll start with distance versus displacement, then cover speed, velocity, and graphs, move into the acceleration escalation, learn the equations of motion, and finally wrap up with predicting the future.
Section 1. Distance versus displacement. So, what exactly is the difference?
Well, here's the answer to our sheep problem. If you said the sheep traveled 25 kilometers, you calculated its distance. Distance is just the total length of the path taken. You simply added 10 plus 5 plus 10. Easy enough, right? But if you looked at where the sheep started and where it actually ended up, you'd realize it only moved a net of 5 kilometers south. That is called its displacement. Displacement is literally just the net change in position. It couldn't care less about the zigzagging path. It only cares about where you started, where you finished, and in what direction. And we can track this whole displacement concept mathematically on a simple number line. In physics, positive and negative signs aren't just abstract math. They literally dictate the direction of your displacement. If an object moves to the right, it's a positive displacement. If it moves left, it's negative. By simply adding up these positive and negative shifts, we can easily pinpoint our final net displacement. Direction is absolutely everything here. Moving into Section 2, speed, velocity, and graphs. Let's see what this motion actually looks like. Take a look at these race stats between two friends, Mervin and Nishal. They both ran a 6-meter displacement. Now Mervin started at 0 seconds and finished at 6 seconds, which means he traveled 1 meter every second. So his velocity? 1 meter per second. But Nishal? She wasn't even at the starting line at 0. She started 2 seconds late, but crossed that finish line at exactly 4 seconds, meaning she covered that exact same 6-meter displacement in just 2 seconds. That gives her a velocity of 3 meters per second. She clearly wins the race. And we can visualize this perfectly on a position time graph. Think of it kind of like climbing a mountain. The steepness of the line, or the slope, directly equals the velocity. A steeper slope means a much faster change in position. So at a mere glance, you can just look at a really steep line and know immediately, okay, that object is absolutely flying. Now, finding average velocity over a few seconds, that's pretty easy. But what if you want to know your exact velocity at a single frozen fraction of a millisecond? When we try to pinpoint instantaneous velocity down to a specific moment, we hit a massive paradox. You see, to find velocity, you have to divide a change in distance by a change in time. But in a single frozen instant, the change in distance is 0, and the change in time is 0. You literally get a 0 divided by 0 paradox. This blew the minds of the ancient Greeks. They questioned reality itself, wondering if motion was just an illusion. Luckily, centuries later, this exact problem inspired Sir Isaac Newton to invent a completely new branch of mathematics just to solve it: calculus.
Which brings us to Section 3, the acceleration escalation. What exactly happens when speed isn't constant?
Look, I know you want to use the simple speed equals distance divided by time formula. It's safe, it's comfortable, but unless you're like our friend Vinayak, driving a car in perfectly uniform circular motion, where the speed never ever fluctuates, you absolutely cannot use it. The exact moment an object hits the gas pedal or slams the brakes, that formula just completely breaks down. Instead, when speed is changing, we have to measure acceleration. Just look at the difference between a cheetah and a deer here. Acceleration measures how quickly velocity changes. If a cheetah accelerates at 4 meters per second squared, it's gaining 4 meters per second of speed every single second. But a deer accelerating at 10 meters per second squared, that deer is gaining a massive 10 meters per second of speed every single second. It is increasing its speed way faster than the cheetah. Pretty wild, right? Section 4. The equations of motion.
Get ready, because these are your ultimate physics cheat codes.
Remember that calculus we mentioned earlier? Well, if an object's acceleration is constant, you actually don't need calculus at all. Don't let the math intimidate you here, because finding displacement on a velocity time graph is really just a simple visual geometry trick. You literally just find the area under the line. You calculate the area of a rectangle, which represents the initial velocity over time, and add it to the area of a triangle representing the acceleration. Boom! You've just derived the formula for displacement without touching a single drop of calculus.
And that geometry trick leaves us with 3 magical equations. Let me formally introduce you to them. The first one lets you calculate final velocity. The second, which we just looked at, calculates displacement. And the third, that is a brilliant shortcut that lets you solve for variables even when you don't know the time. As long as the acceleration stays constant, these 3 equations are absolutely the keys to the kingdom.
Finally, Section 5, Predicting the Future. It is time to solve some real-world mysteries with our new tool belt. Whether it's a cheetah speeding up from rest or a massive train slamming on its brakes, our absolutely crucial first step is to simply extract our given variables from the scenario. If a cheetah starts from rest, its initial velocity, or u, is 0. If a train is braking, its acceleration, a, is negative, in this case, negative 8 meters per second squared. And if it comes to a complete dead stop, its final velocity, v, is 0. Once we write down exactly what we know, we just pick the equation that perfectly fits our missing puzzle piece. But what happens when we tackle a complex problem where you just don't have enough information for a quick one-step solution? Imagine a tortoise accelerating from rest to 40 meters per second, covering a distance of 100 meters. If we want to find out how long that took, we hit a brick wall. We don't know the time, and we don't know the acceleration. But by logically choosing our time-independent equation first, we can easily solve for acceleration. Then we just plug that new acceleration right back into our first equation to find the time. 2 steps, total physics mastery. And after crunching those numbers, it remarkably takes just 5 seconds for our accelerating tortoise to hit 40 meters per second and cover 100 meters. Now that is one seriously fast tortoise. So you are now fully equipped. You've got the physics tool belt to track distance, displacement, speed, velocity, and predict the exact future of any object experiencing constant acceleration. But I'm going to leave you with this final universe-bending question. What do we do when the acceleration itself starts changing? What if the rate at which you speed up actually speeds up? Think about it and keep exploring.